Hi all. So in this video lecture, we will discuss about different types of flip-flops normally we are using in our digital circuits. Normally all the flip-flops are available as ICs. So actually in these ICs we are using a number of gates for developing the flip-flops. Okay. So basically 4 types of flip-flops are there. That is SR flip-flop, D flip-flop, JK flip-flop and T flip-flop. So first we will discuss about SR flip-flop. This is the representation of an SR flip-flop. This SR flip-flop will have two inputs S and R. We can call it as set and reset input. Okay, S and R are the corresponding inputs, and also a clock input is also there. So it is a clocked flip-flop. SR flip-flop is a clocked flip-flop. Okay, so by viewing this clock pulse, we can say it is a positive edge triggered clock. Okay, positive edge, because the state transition occurs at 0 to 1. Okay, so it is a positive edge triggered flip. Also the positive edge triggered is represented as just like an arrow. If it was a negative edge triggered flip flop, then the arrowhead will be at the edge of 1 to 0. Okay, at the edge of 1 to 0, and also there will be a bubble, okay, in front of this arrowhead. Okay, so this is an SR flop, and two output will be there, Q and Q bar. And next we are moving to the detailed truth table of an SR flip flop. Okay, so in the first column it represents the positive edge trigger. It is for showing it is a positive edge triggered flip flop. The clock is showing here. Okay, up arrow means it is a positive edge triggered flop. Down arrow means it is a negative edge triggered flop. So here we are considering it as a positive edge triggered one, and S and R are the corresponding two inputs, and Qn is the present output of the flip-flop before applying this S and R, and Qn plus 1 will be the next output level. That is, Qn plus 1 will be the output after applying this S and R inputs. Okay, and the last column represents the state. Okay, so for the first case, when S and R are 0, 0, S and R are 0, 0, the state is no change. No change means the output of the flip-flop will continue its state. Okay, that is, when S and R are 0, 0, suppose the present output of the flip-flop is 0, it will continue its state. The next state also will be 0. Okay, and also there may be another condition. The present output may be 1. Okay, at the time of giving this S and R as 0, 0, the present output may be 1. Okay, so in that case it will continue its state. So the Qn plus 1 with the next state after applying 0, 0 will be 1. Okay, so for S equal to 0 and R equal to 0, the state will be no change. The output of the flip-flop will continue its state. If it is 0, it will keep on remaining it as 0. If it is 1, it will remain it as 1. Okay, and for the next case, when S equal to 0 and R is equal to 1, always the output will be in reset condition. That is, the output will be 0. Whatever may be the prior output state, the next output level will be 0. Okay, that is, for S equal to 0 and R is equal to 1, if the prior state, the present state is 0, the output will be 0. The next level will be 0. Next output will be 0. And if the present output is 1, then also the next output will be 0. That is, if you are applying S equal to 0 and R equal to 0, always the next level, that is the output will be 0. And for the third condition, when S equal to 1 and R equal to 0, always the output will be 1. Whatever may be the present output level, the next output level after applying this S equal to 1 and R equal to 0 will be 1. That is the set condition. Okay, and for the fourth case, when S equal to 1 and R is equal to 1, it is an invalid state. For an SR flip-flop, we are considering it as an invalid state. It is not, it is an indeterminate state. Okay, so that is the main disadvantage of an SR flop. It will not work. We can't predict the output level for S equal to 1 and R equal to 1. Okay, so this is just like an example the output waveforms and input waveform of an SR flip-flop. Okay, this is the clock pulse we are applying, and it is a positive edge triggered clock because the arrow is shown here, that is 0 to 1 transition period, and this is the S input we are applying to the flip-flop, and this is the R input. Okay, the S input, for some time it is 0 and it is again 1, it is 0, it is again 1, like that. Okay, and Q is the output of the flip-flop and Q bar is the opposite output of the flip-flop. Okay, two output will be there, Q and Q bar. Q bar is just opposite of Q. Okay, so let's have a look of this timing diagram. That is at the initial condition, this S equal to 0 and R equal to 0, and we are assuming that the Q, the output of the Q at the present output we are treating it as 1. Okay, the present output we are assuming that the present output it as 1, and we know that it is a clocked flip-flop. The output will change its state. Okay, the output will change its state only at the clock transition period. That is, without a clock pulse, the S and R inputs cannot affect the output. Okay, so only with this clock pulse, the S and R will affect the output. Okay, so for the first clock pulse, at the time of first clock pulse, the flip-flop will check its inputs. That is, at the time of first clock pulse, that is at the positive edge triggered time, S is 0 and R is 0. For S is 0 and R is 0, we know that the state is not changing, so the flip-flop output will continue its state. So the present output we are assuming it as 1, so the output will continue its state, it has 1 up to the next clock pulse, at the time of next clock pulse, the flip-flop again check its inputs. So at that time, S equal to 0 and R is equal to 1. For S equal to 0 and R is equal to 1, we know that always the output will be 0. Okay, so at that time, the flip-flop will change its state from 1 to 0. Okay, so at the time of the second clock pulse, S equal to 0 and R is equal to 1, so the flip-flop will reset its condition, that is 1 to 0 change, and it will keep on its state as 0 up to the next clock pulse. At the time of next clock pulse, the flip-flop will consider its inputs. At the third clock pulse time, S equal to 1 and R equal to 0. For S equal to 1 and R equal to 0, we know that the output will always be 1. Okay, it will be in set condition. So the output of the flip-flop is again changing from 0 to 1 and like that. Okay, so this is for understanding the operation of an SR flip-flop. Okay, so the simple truth table of a flip-flop can be written as like this. For S equal to 0 and R equal to 0, the Qn plus 1. Okay, that is the output after giving this input, that is Qn plus 1 will be Qn. Okay, that is no change condition. Whatever may be the Qn for the inputs S equal to 0 and R equal to 0, it will keep on like that. Okay, for S equal to 0 and R is equal to 1, Qn plus 1 will be 0. For S equal to 1 and R equal to 0, the Qn plus 1 will be 1. For S equal to 1 and R equal to 1, it is an invalid state. So that's about our SR flip-flop. And also this is the internal diagram of an SR flip-flop. We are using 4 NAND gates for developing an SR flip-flop, and also a pulse transition detector will be there for detecting the edge triggered clock pulse. Okay, and this is the Q output and this is the Q bar output. So you have to learn this figure well. Okay, and next you are moving to the D flip-flop, edge triggered D flip-flop. Okay, here we are also considering it as a positive edge triggered D flip-flop. Okay, so for a D flip-flop, only a single input will be there, that is D will be the input, and based on that input, two output will be there, Q and Q bar. Okay, so D can be treated as like this, that is it's an SR flip-flop, and we are giving an input D to S and also another input D bar. Actually we are using a NOT gate here. Actually we are giving this D bar to the R input of an SR flip-flop. Okay, so we can also treat that D flip flop, the internal circuit of a D flip flop, just like an SR flip flop having a NOT gate. Okay, so it's for simply understanding the circuit, and this is the detailed truth table of a D flip flop. So by observing this, when D is 0, when the input D is 0, the output always will be 0. So output depending upon mainly on the input D, whatever may be the prior inputs, whatever may be the prior output of the flip flop, the next output level after applying this D, the next output level will always be 0. And also for another condition, for D is equal to 1, whatever may be the prior output, always the output will be 1. So only two conditions are there. For D is equal to 0, output will be 0. For D is equal to 1, output will be 1. Okay, and this is the truth table of a D flip flop. For D is equal to 0, Qn plus 1 will be 0. For D is equal to 1, Qn plus 1 will be 1. Very simple. And next we are moving to the JK flip flop. For a JK flip flop, J and K are the inputs and Q and Q bar will be the output, and it is also a clocked flip flop. It is also here we are considering it as a positive edge triggered 1. Okay, and this is the detailed truth table of a JK flip flop. It is just same as our SR flip flop, only the difference is J and K. When J is equal to 1 and K is equal to 1, we can determine the output. Okay, that is the only difference here. So let's have a look of the truth table. For J is equal to 0, K is equal to 0, whatever may be the prior output, the next output will level, that is, it will not change its output. Okay, so here it is not 0, it is 1. It's a small false here. For the first case is Qn is 0, Qn plus will be 0. Second case Qn is 1. So here it is 1. So here it is 1. Okay, and Qn plus will be 1. So for J is equal to 0, K is equal to 0, the flip flop will not change its output. For J is equal to 0 and K is equal to 1, whatever may be the prior output, the next output after applying this input will be 0. Okay, same as our SR flip flop. For J is equal to 0, K is equal to 1, our output will be 0, reset condition. For J is equal to 1, K is equal to 0, our output will be, always the output will be 1. Whatever may be the prior outputs, always our output will be 1. It is in set condition. Okay, and the last condition is defined here for a JK flip flop, that is for J is equal to 1 and K is equal to 1, the output will toggle. Okay, suppose the previous output, the prior output of the flip flop was 0. So when we are applying J is equal to 1 and K is equal to 1, so the output will toggle to 1. Okay, the prior we are considering, prior output was 0. So after applying J is equal to 1, K is equal to 1, the output changes from 0 to 1. Okay, and also if you are considering, if you are assuming that the prior output of the flip flop was 1, so after applying J is equal to 1, K is equal to 1, the flip flop will change its state from 1 to 0. Okay, so the last condition is a toggle condition. Okay, so this is the truth table of a JK flip flop. For J is equal to 0, K is equal to 0, Qn plus 1 will be Qn, same as our SR flip flop. For J is equal to 0, K is equal to 1, Qn plus 1 will be 0. For J is equal to 1, K is equal to 0, Qn plus 1 will be 1. And for J is equal to 1, K is equal to 1, Qn plus 1 will be Qn bar, toggle condition. Okay, so this is the timing diagram of a JK flip flop. This is an example of a JK flip flop. Okay, by observing the truth table, we can simply understand the working of a JK flip flop here. So here the clock pulse is a negative edge trigger. So here for understanding, we are just considering it as a negative edge trigger flip flop. That is, the flip flop changes its state only at the negative edge trigger time. Okay, and also we are assuming that Q, our previous output Q as initially, we are assuming it as 1. Okay, and we are observing at the first clock pulse. Okay, at the first negative edge trigger clock pulse. So at that time j is equal to 1 and k is equal to 0. For j is equal to 1 and k is equal to 0, we know that the output will be 1. Okay, so the output will continue it as 1 up to the next clock pulse. Okay, up to the next clock pulse. So in the next clock pulse, j is equal to 0 and k is equal to 1, and we know that for j is equal to 0 and k is equal to 1, the output will be 0. So the flip-flop will change its output from 1 to 0. Okay, so like that we can understand its operation. So this is the internal diagram of a JK flip-flop. So here we are providing a feedback, okay, extra feedback to the first NAND gates. Okay, first, so for NAND gates will be G1, G2, G3, G4. Okay, only difference from a flip-flop is that we are giving a feedback from the output to the first and second NAND gates. Okay, you have to learn this figure also. And the last one is T flip-flop. Okay, T means toggle. Okay, T flip-flop also have a single input and two output Q and Q bar. Okay, and T flip-flop also can be considered as a JK flip-flop having the two inputs are same. Okay, we are giving all the single input to both the inputs of a JK flip-flop. Okay, so T flip-flop can be considered as a JK flip-flop having the same input at both the inputs. Okay, and this is the truth table of a T flip-flop. Here when T, this is T, not J, this is T. Okay, when T is 0, the state will not change. That is, the output of the flip-flop will not change. Whatever may be the previous output, it will continue it as like that. Okay, if the previous output, if the prior output was 0, Qn plus 1 will be 0. If the prior output is 1, then Qn plus 1 will be 1. Okay, for T is equal to 0, the flip-flop will not change its state. And for T is equal to 1, the flip-flop will toggle its output. Okay, if the prior output was 0, the next output will be 1. If the prior output was 1, the next output will be 0. So for T is equal to 1, the flip-flop will toggle. Okay, and this is the truth table of a T flip-flop. For T is equal to 0, Qn plus 1 will be Qn, and for T is equal to 1, Qn plus 1 will be Qn bar. That is toggle condition. Okay, so that's about our 4 types of flip-flops. Okay, that is SR, D, JK and T flip-flops. Thank you.